Local trajectory stabilization for dexterous manipulation via piecewise affine approximations. How to enable robots to manipulate objects dexterously like human hands do is a long-standing problem. Alongside hardware, perception, and planning, motor control is one of the challenges in manipulation. Designing reliable feedback controllers for manipulation is hard due to the nonlinear and context-rich nature of the manipulation tasks. For example, how should we design a controller for the robot to flip carrots like humans do? This is more than a simple pick-and-place task, and indeed, even an experienced human operator teleoperating the robot often cannot succeed in one or two tries. In general, there are two main categories of approaches to control design for manipulation: model-based approaches and learning-based approaches. Model-based approaches have mainly been applied to grasping and planar pushing. On the other end of the spectrum, learning-based approaches have been applied to tasks with greater variety and difficulty, ranging from reaching, grasping, planar pushing, to rotating a rod, throwing objects, rotating a cube, and even solving Rubik's Cube. Although learning-based approaches have been successful on tasks that model-based approaches have not been able to solve, they lack reliability or stability guarantees. Motions of manipulators are unpredictable, especially for those whose policies are represented by deep neural networks. Judging the usefulness of such control policies is always empirical. In this paper, we try to push forward with the model-based approach. In order to achieve the dexterity of a human hand, we want the robot to do tasks more complicated than grasping or planar pushing in a feedback fashion. The task we are considering is how to enable the robot to flip carrots like humans do. In order to get a feel of how hard it is for the robot to flip the carrot, we ask an experienced human operator to teleoperate the robot, trying to flip the carrot. The carrot was replaced by a half cylinder. We observed that the experienced human operator often cannot flip the carrot in one or two tries. We formulate the problem as steering the joint robot object system, which is a non-smooth nonlinear system, to the target region from an initial state. Our approach consists of three steps. First, we plan a trajectory via nonlinear trajectory optimization. Second, we linearize around the nominal trajectory to get local piecewise affine systems, and we build funnels around the nominal trajectory. Finally, we solve linear programming online to check the nominal trajectory. We use our algorithm to design a trajectory that flips the half cylinder 90 degrees so that the grippers are holding the half cylinder. After that, a manually designed open loop controller will transport the half cylinder and flip another 90 degrees. We mainly focus on the first 90-degree rotation for several reasons. First, it is the most challenging in the entire manipulation process, and the manually designed open-loop controllers as well as the experienced human operator usually fail in this phase. Second, in the next 90-degree rotation, the dynamics is different from that in the first 90-degree rotation, so we need to design a different trajectory separately instead of simply extending the first trajectory. Besides, it is very simple to design a good open-loop controller for the next 90-degree rotation. We model the half cylinder as a half disk and the parallel gripper as two rectangles. The state of the system is x, y, theta, x dot, y dot, theta dot, phi, and w. X and y are the coordinates of the center of mass of the carrot. Theta is the angle between the flat surface of the carrot and the ground. X dot, y dot, theta dot are the time derivatives of x, y, and theta respectively. Phi is the angle between the gripper and the horizontal axis. W is the distance between two grippers. The control input includes the normal and the frictional forces between the gripper and the carrot and those between the carrot and the ground. It also includes phi dot and w dot, which are the time derivatives of phi and w respectively. We use the direct transcription method to set up a nonlinear trajectory optimization problem. The loss function is the angle between the gripper and the flat surface of the carrot. The first two constraints are the Newton-Euler equations. We also have friction cone constraints, contact constraints, kinematics constraints, time integration constraints, and so on. In the trajectory planning, we borrow the idea of zero moment point, or ZMP, for bipedal footstep planning in the humanoid robot literature. For a bipedal robot walking on the ground, ZMP is by definition a point on the ground where the sum of all the tangential moments equals zero. Although many humanoid robots have pressure sensors on the feet, because of lack of reliability in the case of Atlas, researchers do not measure ZMP directly. What they do is to plan a joint ZMP and center of mass trajectory and then only check the center of mass trajectory during online execution. Similarly, in the trajectory optimization formulation, we use forces as part of the control input. In the manipulation context, the forces are those between the gripper and the object and those between the object and the environment, for example, the table. Although the hardware we are using cannot directly measure the force it applies to the object, we still use forces as control variables to help plan the center of mass trajectory of the object as well as the post trajectory of the gripper. During online execution, we only check the trajectory of the center of mass of the object and that of the gripper. We solve the trajectory optimization using off-the-shelf numerical solvers, and we get a trajectory x0 bar, u0 bar, x1 bar until xn bar. Next, we linearize around the nominal trajectory. Because the gripper can make and break contact with the object, which results in different system dynamics, we get a piecewise affine system around each nominal point. We build a polytopic funnel around the nominal trajectory based on the local piecewise affine dynamics models, and we show that if the system state is inside one of the polytopes, then the controller is guaranteed to steer the original non-smooth, non-linear system into the target region. During online execution, it is likely that the system state is outside of the funnel due to the inaccuracy of the model, the stochasticity of the real world, or external disturbances. So we solve linear programs online based on local piecewise affine dynamics models to steer the system back to the funnel or to the nominal trajectory. This is our feedback controller. In comparison, here is an open-loop controller that simply executes the nominal trajectory without the feedback component. It fails under external disturbances. The feedback controller recovers from external disturbances. There are two kinds of disturbances. The first kind is that the carrot is pushed by a human hand. The second kind is that the gripper suddenly opens up. The feedback controller can even recover from very large disturbances that violate our design assumptions.